Hi everyone, my name is Hongyan. I'm a PhD student at University of California, Los Angeles. I'm presenting our paper entitled Augmenting Pathologists with NaviPath, Design and Evaluation of a Human-AI Collaborative Navigation System. I would like to acknowledge and thank our collaborators from University of Kansas Medical Center, Beijing Torrent Hospital, and UCLA David Gavin School of Medicine for their contributions to our research. One of the crucial steps in diagnosing cancer involves pathologists sorting through optical microscope for patterns of interest. With digital pathology, tumors can now be scanned into high-resolution digital images, as shown in the red figure. However, these digital scans can be high-dimensional, making it challenging for pathologists to navigate. Over the past decade, multiple studies in SIGCHI have sought to address this issue. These solutions can be grouped into three major categories. 1. Utilizing specialized hardware. 2. Proposing novel interface designs. And 3. Leveraging the power of artificial intelligence. Prior research has shown that utilizing a human-AI collaborative approach can result in improved accuracy and efficiency for pathologists. Inspired by the success of previous solutions, our current work aims to propose a human-AI collaborative system that enhances pathologist navigation. Moreover, we aim to go beyond previous human-AI solutions by incorporating pathologists' domain knowledge and considering their workflow integration in practice. Our goal is to develop a system that not only improves the accuracy and efficiency of cancer diagnosis, but also seamlessly integrates into pathologists' current practices. To accomplish the goal, we conducted a formative study to identify pathologists' navigation preferences when searching for the pathological pattern of mitosis. Our study yielded 3 key observations. Using these insights, we collaborated with pathology experts to design our human AI system. Our iterative design process included creating low-fidelity prototypes, refining them into high-fidelity versions, and ultimately developing a fully operational system. We named it NaviPath. To reflect the 3 key observations in the formative study, we incorporated 3 main design features. First, hierarchical AI recommendations. Second, customizable recommendations based on multiple criteria. And third, queue-based navigation for high magnifications. NaviPath provides 3 levels of AI recommendations that vary in their level of detail, echoing pathologists' navigation preferences. These recommendations include 1. Local recommendations, which are visible even at low magnification and support pathologists in their initial overview of the scan. 2. Hyperfield recommendations, which are designed to assist pathologists when examining the scan at high magnifications. And 3. Cell recommendations, which has the highest level of magnification to aid pathologists in determining whether a suspected cell is indeed the target. To generate the recommendations, NaviPath utilized 3 AI-reported criteria: cellular count, proliferation probability, and mitosis count. These criteria can be customized by adjusting their prospective impact on the recommendations. The system assigns greater weight to a specific criterion when its impact is increased, resulting in more emphasis on that criterion in the generation of recommendations. Moreover, NaviPath continually recalculates and re-ranks the recommendations in real time based on the pathologist's customization settings. To further improve pathologist navigation efficiency, we incorporate the queue-based navigation feature into NaviPath. When in high magnifications, a list of number buttons appear on the edges of the interface, representing the navigation queues that allow pathologists to jump to remote recommendations. Each button corresponds to a specific recommendation, and its location indicates its relative position to the current view. By simply clicking on each button, pathologists can jump directly to the relevant recommendation. NaviPath is implemented as a web-based system accessible through any web browser. The system can run on screens of various sizes, ranging from 12-inch tablets to 65-inch TVs. Moving on to the evaluation of NaviPath, we assign the task of mitosis evaluation to pathologists. Mitosis is a pathological pattern that is crucial to patient prognosis, despite its small size in digital pathology scans. It is worth noting that each mitosis typically occupies only about 40 pixels. Given that a single pathology scan may contain up to more than 7 gigapixels and about only 400 mitoses in total, locating mitosis can be a challenging task for pathologists. We recruited 50 medical professionals in pathology from 5 medical centers. We compared 3 conditions: manual navigation, examining with NaviPath, and AI automatic reporting. We measured the efficiency and accuracy of each condition. Our results show that pathologists achieve significantly higher efficiency with NaviPath compared to the manual navigation, seeing more than twice the number of mitoses in unit time on average. Regarding the performance of mitosis identification, we measured participants' precision and recall in detecting mitotic figures. The results show that, compared to the manual navigation, participants' precision and recall in identifying mitosis was significantly improved with NaviPath. Additionally, compared to the AI, participants' recall and precision was improved by NaviPath on average. We discovered that participant recalls or sensitivities can be higher with NaviPath. We believe there are two potential explanations for this improvement. First, NaviPath recommendations have higher prevalence rate of mitosis. Compared to the areas visited by the manual navigation, NaviPath recommendations have more than 6 times the chance of containing a mitosis. Previous research in visual search suggests that the low target prevalence can cause a shift in decision criteria, leading humans to miss targets in the visual search. Therefore, participants may not have performed as well in the manual navigation due to the low prevalence rate. Second, NaviPath AI recommendations can highlight mitosis with higher sensitivities. With AI recommendations, pathologists' tasks shift from visual search to verification, which is generally an easier task. As shown in the right figure, NaviPath also supports doctors in adjusting their sensitivity of recommendations. During our study, we found that the majority of participants prefer to set the sensitivity to the highest level, enabling NaviPath to recommend as many boxes as possible. Even if there are false positive recommendations, doctors may quickly rule them out, improving sensitivity. In terms of future work, there are 3 areas of improvement that we plan to address. Firstly, as NaviPath uses deep learning models for recommendations, its behavior may not be always predictable. Making AI more predictable will benefit the users. Secondly, the current system does not support users in adding self-defined regions of interest, enabling that in the future could provide users with greater flexibility. Finally, the current queue-based navigation may be confusing at times because it does not provide distance information. We plan to provide the navigation queues to be more informative for users. In conclusion, NaviPath as a human-AI collaborative system can augment pathologists' navigation efficiency and performance. We hope that our system can be further improved to support pathologists in diagnosing cancer and improve patient outcomes. Thank you for your attention, and I welcome any questions or comments.